Okay, Dequan, you can start.
Okay, thank you, Lev, for organizing this seminar. I'm really honored to be here. Today I'm going to talk about transformers. First about myself, my name is Dequan. I'm currently a data scientist at NDR. You can reach me at the Gmail or my LinkedIn page. So today's topic is like the transformers. It's almost everywhere, like the base for that. You heard a lot of BERT, GPT, a lot of things like ChatGPT. So we're going to talk about what's the underlying thing, how it develops. So this is the outline. We are going to do an introduction and do model architecture. I'm going to focus a lot on some mathematics or how this model is different with other like previous models and why this developed into the blossom of such the GPT stuff. And also we are going to review what's the derived models and also possible applications. All right, so first the introduction. About the before the time of transformers, there's already many of these models like the RNN model or LSTM model or GRU model. I guess most of you guys already know that. But why this is coming up? Like in 2017, a team from Google, they were doing it. Most of the reason is for natural language processing. Suppose you have a sentence and then you're trying to either translate or understand what the sentence means, or more like genetically, you can generate your own view or using the GAN like stuff to generate an answer to a question. But before this, there is some pinpoint for the other model structures. Number one is it's harder for the like RNN model or LSTM model to parallelize. I mean, that is because their structure, there's a sequential models. I will explain it later. And number two is if you want to get a better idea of a whole paragraph or you expand the whole universe of languages, your computing power is limited by the model structure. How can we get a better model that can capture more sentences or more content on the web? That's the thing. And yeah, by doing this, we previously know that encoder and decoder model work pretty well. That's majorly how your Google Translator is working from one language to another. They use kind of a hidden state at a certain time, and you know the previous time hidden states. And you keep doing that until you train into your recurrent neural network. So also they have the problem of the long sequence memory loss. Basically, say you have a 3-word sentence, that's very easy for model, but if you have 30,000 word sentence, that's pretty hard because you need to wait for the previous blocks to finish it, and then you can start. So attention model is similarly kind of borrowing the idea, but it solves the problem by extracting all the information at once. So yeah, so in this review, we're going to see how it did achieve that, and also above it, why it is fast, why we can parallelize it, and based on the development of transformers, what are the variants like the BERT, the GPT, and recently very popular ChatGPT. And also this thing can be expanded from the original NLP into audio, into picture, into video thing. It's a very cool concept. So let's dive into this. So we know first we want to talk about the encoder-decoder structure. Let's say here you have a language with 3 words, and after the embedding of it, you're converting a word using your dictionary into some value, and then these values can be trained by a model, and that's called encoder, and you save those dictionaries and the model will help you to output that as a decoder. So the lengths of encoder and decoder are not necessarily the same because maybe you're translating from English to French, their length for the same meaning would be different. And that's a very good example. So based on that, in 2017, the Google team has developed this attention, like this model. The title is very interesting, called "Attention is All You Need." Here, well, I mean, their attention exactly was meaning this multi-head attention layer, but beside that, you need also the other layers as an ensemble to make this model work. If you only have this layer, it's never going to work. So we're going to talk about how this model works. And I think a good plotting, which this one did, clearly shows us how this works. So basically, remember, compare with the encoder-decoder thing, we have the same thing. The left-hand side with the encoder and right-hand side is the decoder. Basically, your input at the very beginning was kind of a sentence. And then your output is output the probabilities that projected the sentence into a word space. So that's basically another sentence, but in different language or in the same language in a different way. So how they're doing it. So there are several components we're going to examine part by part. So first, let's see some overall thing. The N here, you see on the block, there are the N. So that's repeated, how many repeated layers you have. In this original paper, they have N equal to 6. Basically, you stack this stuff 6 times and they got to stack the model. So first thing first, you have the word or the sentence coming as your input, and then using the embedding layer, each of the word is converted into a vector in your word space. And you can calculate their Euclidean distance or whatever, give them a value. Basically, let's say hello world, these 2 words, after this embedding layers become 2 numbers or 2 vectors. And how large is this vector is depending on like the corpus you want to deal with. That one is here set 512. That's their settings. It can be longer or shorter. So the shorter, which means in your dictionary you have less word. But here you transform that into a certain type of value. By value, I mean here your input is quite 3 things. From a sentence, you can generate 3 things. Like this. So basically, let's come to the first part, the attention layer. So the attention mechanism works like this. You have a query which asks for the key value pairs. Let's say you query a thing and then you query a particular word, and each of the word has its own value. So different queries, they have different similarity. Let's say query 1, your query around this key. All right. So this key, your query would be similar to this key more than other keys. So how you want to calculate the similarity, then you do the dot product, which is a q.k, that is your query and dot your keyword. So then this is the cosine, basically how close they are. If the cosine is 0, no, if the theta is 0, cosine is 1, then they're very close. Otherwise, they're kind of orthogonal. So in such a way, you can determine the weights of each of the similarity weights. I mean, between the query and each of the key. And here you see this is very strong, this is medium, and this is very small to a different key. So the same applies to the query 2. And when you have the 3 input, which is the 3 head of here, the 3 arrows, Q, K, and V, you're putting that into the attention layer. So by calculating it, after calculating this, you get 1 value, and then you do N norm. So that's as a layer norm instead of batch norm. So let's see how they actually achieve this. So it's kind of simple. They have an attention formula. Basically, you do the KQ dot product, calculating the similarity before your query and your key. And then you normalize it by the dimension of your key. Let's say you have a 512, that's your dimension. But if your dimension become really large, let's say then this QT, the number is large. Let's say it's close to infinity. And then you see one problem for softmax is when it's positive or negative infinity is very close to the 0 or 1 side. It's very hard to distinguish. So then you have to scale it down by dividing the square root of dk. And then here you normalize it into the softmax. So each of the word each of this then you will have a value. And depending on how many key you have this same amount of values. And then your amount, the value amount will be multiplied by the V, which is the value for each of the word. And in such a way, here you got one called scale dot product attention. And this is your attention score at this level. So in order to mathematically justify what I said, so here using Q, let's say you have n input as your sentence, and each of them has a dimension of k, dk. And then you do the dot product, and that's it's your keywords. That's not necessarily need to be n, it can be m, a different value. So you do dot product, and then here you have n product m, the dimensionality of this, which is the qk. And also here, since this is dimension is n product m, and here you have a m product dk as your v, and you then multiply them, that will be n by dk. So this gives you the attention value for each of the word input. So let me pause here. Do you guys have any questions so far? Okay, I assume you got this basic idea. So now this is one component, like the attention layer. So then in the model, they're called it a multi-head attention. What is multi-head is basically this layer, you stack them several times and do the concatenation. And each of them is a projection from a linear space. So basically your VDK, their high dimensional space, first you project them into linear and then go to the attention layer and then concatenate them together. So here you use H in this paper, they equal to 8. So basically they gave you 8 opportunities to find a good way of attention. Let's say you gave a sentence, it can have various values. So they let you attempt several times and concatenate that and get the best result. So here there is also a mask layer I skipped. So in this operation, the mask is optional because if you look at this closely, here into the encoder part, you don't have mask, but in the decoder part, you have the mask, the multi-head attention. Why is that? Because in your sequence as a word, as a sentence, when you are doing the sequential thing on a let's say third of your word, you can only see the previous one, the words, but after that you shouldn't see that because that's how you want to make your recurrent training. Like although this one don't have recurrent, it's distill all the information at once, but then you want to preserve the sequence of the word. So that's why how you want to mask it. Okay, so let's go to the next slide. The next component here is the feed forward layer, which is called FFN. That's quite simple. It's basically a multi-layer perception structure. You have a ReLU over here, and that shrink it and shrink it back. So this is the ReLU part. They expanded, they have the input size, let's say n, and then they expanded with one single layer with 2n, and then shrink it back to n. So then using this, and you add additional layer for normalization, and they have some dropout onto that, so you can prevent your model of overfitting. So another component is the positional encoding. So basically, until now, we are not seeing the sequence information because using this attention layer, the sentence will be distilled at once. By saying that, like using the multi-head attention, you got all the information you need from that sentence. Even though you shift or swap the sequence of some of the words, you still got all the thing. But that's not what we want. It's because the sentence is sequenced. So then we encode each of the position into their value as well. So that's how you do this positional encoding. With that, I would say that's the major part of the model architecture. So you have the input, you embedded them, and then you do the encoding, let model see where the sequence of the word, and then feed into the encoder, and then here those values. The output here, here is the pair of Q, key, and V. So that's basically itself, the query itself. And then you with that query, you have the mask query and go back into the decoder thing. After that, you just project it into a linear thing and then do a software max into your word dictionary. So that's how it works. So why this is an advantage to the previous model. So one thing I mentioned is the previous model is sequential training. Let's say the recurrent neural network. You have the word, you have the word coming, you have this hidden layer, and then their output will be the input for the next layer. So in such a way, you have to wait for the previous to finish. So it's very difficult to do parallelization. But here, if you see this attention layer that can distract all the information of the sentence at once, so then it's easy to parallelize it. So that's the major reason why transformer become the foundation for many other models. So in the paper, they talk about the results doing the blue English to French and also English to German translation score. We can see the transformers, they have a standard and also a big one. They are all quite good. The score, they are like exceed all the previous models. And also they work on the WSG dataset. They have a quite good performance as well, you see. So that's the basic idea of how the transformer works. Yeah, so I think this, by understanding why the transformer is advantageous to other things, so we can see that there's a potential develop opportunities. So there is a transformer. The first thing was developed by Google, but then the Hugging Face, that one is an open source, then you can do your own. One thing I forgot to mention is the transformer is kind of a pre-trained thing. You can pre-train that transformer. That enables transfer learning. Like BERT is kind of doing the same way, and GPT and GPT-3, they're just growing exponentially large with the same idea of transformer. And recently the ChatGPT, that's quite popular. People see a lot of applications based on that. we can have an example, say, because ChatGPT is basically parsing all the available sentences online. It's a huge word, and then they train using this model of transformers, and then they can answer your questions. For example, if you want to do a introduction or whatever, write a letter, they can use similar way what you find on the search engine like Google. And also they can work not only on those plain languages, but also they can work on the programming. This example tells you how this chat GPT can help you to debug. It's very interesting. I encourage you guys to search that on the GPT website, and they have a lot of other applications. Also, the first version of the transformer was used to do natural language processing, but after we learn the mechanism, it can be expanded not only into the NLP, but also into videos, into pictures. Let's take a look at the example. See, this is why the transformers are more advantage, and why we use things based on that. So some other developments, let's say the vision version of transformer is before we have seen, we examine the picture by different block of filters. We see that block by block, but here using the same idea of transformer, you can kind of examine the picture at once. A similar idea to YOLO, but it's not exactly the same. But they have something that you can exponentially make your picture reading fast and make it parallel. So then on the video and also the audio part, they also make some progress. You can search online. That's really helpful. And this video stuff is another variant of the transformers. Yeah, I think that's all my presentation. Please let me know if you have any questions.
Well, Dequan, first of all, thank you. And transformers is a difficult topic, and most people really don't understand how they work, me included.
Yeah, this is hard, very hard.
But I can try to give some like imagery to try to understand it. So suppose you have a simple sentence like a man goes home, right? And then you convert each word into a vector, right? Then you do the same for two languages, let's say English and French, right?
Yeah.
And then suppose you have a dictionary which converts these vectors in different languages to each other. So man in English, man in French. Well, it's just regular dictionary, and you just convert word to word. This is like a very, very simplistic translation, right? But then you want to not just word, but maybe neighbors, like close neighbors of the word. And then, so when you converting into vector, you add a layer where you include neighbors, right? And then maybe you include neighbors of neighbors. So you can stack one layer, second layer, whatever, 6 layers. It's kind of what you were describing, right? And so you shift from words into more like groups of words which correspond to some meaning. And if you have a long sentence, then maybe words which are far from the current word are important to get some notion. You know, it's very similar to how our vision works. Like if you look at convolutional neural networks,
yes,
there are layers, and the first layer just detects simple structures like shift from black to white, or a corner, or a line, or like horizontal or verticals. But then you get next layer, and they detect more complex structures. Like, for example, you eventually can get to a node which only reacts if you shown a picture of Bill Clinton or something, right? So that's where this multi-layers are coming from. So you start with one layer, and then this attention mechanism, it tries to calculate for the next layer which words are important. Like, if you, let's say you have 100 words and you are at a position number 44, and you go to the next layer, which will also have 100, let's say, and you want to calculate which other words are important for the word number 44, how are they related. And that's the attention. So for each word, you calculate attention for all other words, how they relate to this word.
Yes.
And that's how you go from layer to layer to layer. And so you encoding to get some representation, which is not representation in words. Representation more is like their connections,
Yes.
how they relate to each other. And so this is a multi-layer encoding. And then there is multi-layer decoding into a different language. I don't know if this description helps.
Yeah, that's helped a lot. Thank you, Lab. I think one thing I really like is the description, like the analogy between this to the CNN. So where in your CNN, you have the filters, and many of the filters, you start to extract picture. Let's say you have a picture. First layer, maybe you're extracting the pixel. And the second layer, you're extracting info into several pixels. And then you're extracting the next layer, you're, let's say we do face recognition. You extract the info for noses, for eyes, for all the edges and the characters. So that's similar idea to here. And as Lev described, we have N stack. The first stack maybe extract the similarity or of some word and its neighbors. And the second layer, the input is the first layer's output. And then their relation between one word and its neighbor is also extracted. So by layer and layer, we can finally got a highly conceptually distilled sense from a very complex sentence, and use that passing into the decoder with the similar structure that really helps. Yeah, I think Lev did explain it really well.
And I want to add something else about BERT. So the first B in abbreviation BERT means bidirectional.
Yes.
And the idea is that, like Dequan was explaining, you need to keep track of the direction of the sentence, right? But also, you need also take into consideration the following words, right? Especially in German, where like there may be a sentence and then the last word in the sentence may change it completely, right? So you have actually to analyze in both directions. And another thing BERT does, it kind of similar to how Fourier transform works. You look at high frequencies or things which are close to each other, and at long frequencies, like slow frequencies, things are far, and you calculate them separately and then combine. That's kind of things which BERT does. It's actually very elegant and but complex. Yeah. And you see 175 billion parameters, GPT-3.
That's astonishing.
Yeah, that's kind of explains why it is complex. I tried to find good images and good diagrams explaining, and somehow I haven't found them. What Dequan was using is the pictures from the original paper from Google.
Yeah, that's what I mean.
Yeah. Anyway, I don't have questions. Guys, do you have any questions? Hello?
thank you. It's a great lecture. Yep.
Thank you.
Yeah, of course. And so far, I don't have a question personally. Just need to analyze this fantastic.
Yeah, this is cool.
Excuse me. Thank you for the lecture. Is any kind of practical example I can see online that would represent transformers and introduce to kind of greatest achievements?
Oh yeah, so there's a couple of examples here. What I want, I encourage you to look at this most recent ChatGPT on their website. You can basically try it, just register things for free, and you can try, let's say this is user typing, like you have this code, have how to fix it, how to find the error, and this is, they took the input and generate the answer, and you keep asking them, they can find this error, the bug for you. That's very interesting. And also some like some using something or asking some questions. I tried that. They gave pretty decent answer. It's similar to you use Google search engine. Basically, the search engine is a pretty like cache a lot of web pages, and then they find the most relevant to you. But here they in the ChatGPT, which is also a variant of Transformer, they kind of parse all the internet, or they access the internet and take that as your input and train the model. That's why they have the 175 billion parameters, and they got pre-trained. You can use that transfer learning, and the answer they gave is quite interesting, I would say.
Thank you.
You're welcome.